You guys have access to it later. Hello, everybody. Welcome. My name is Stephen Youssef. I'm going to be one of your TAs, as you saw in the little intro video before. We also have David Bauman here. David, if you want to say hi real quick.
Hey guys.
There we go. So David will be doing half of the lectures, and I'll be covering the other half. So I'm taking the first two that Dr. Peterson are doing, and we're just going to kind of switch back and forth moving forward. We will send out a schedule with the exact dates of what's going on. We're just trying to work out the semantics here, and we know that the vote was pretty close. So we're going to see whatever we'll do the best that we can to accommodate to everybody. We don't want to, set it up in a way so that only half the class is able to come, so we might end up just doing a little bit of both options. We're still working it out, but we will let you know very soon exactly what's going on. Just a little background before we jump into the material. Guidelines for the Zoom call. If you're not talking, please do put yourself on mute if possible. How do I do this? Anyway, I'm gonna be fumbling around a lot on Zoom. I'm just forewarning you now. I haven't hosted too many meetings. I was a professor of anatomy and physiology at Marist last year. It was great, but it was all in person, so I didn't really have too much of the technological aspect going on. But I'll definitely do my best, and I might have to ask you guys for a little bit of help here and there. But if you're not talking, please be on mute. If you would like to talk, don't got to deal with the whole raising hands business. Don't got to do anything, but just unmute, start talking. Feel free to interrupt me. We're here to help you, whatever you got to do. So also, hello. All right, there we go. Okay, just another little forewarning. I did get a new computer, and as I already mentioned, I'm technologically challenged. I'm terrible with all this stuff, so I'm better with a pen and paper and a whiteboard. So I'm still kind of figuring out how to get the iPad attached, and I'm sure I'll have it by next week's review. But fortunately, there's not too much writing in this one or too many equations. I might have to resort to this bad boy at some point if my thing doesn't blur out, but I don't think we're going to really need it. Are there any questions before we get started, before we just jump right into the material?
I have a question.
Sure.
Like moving forward in the course, do you have any advice or like tips for the best way to study this material for this specific class?
Absolutely. Yeah. I'll tell you what, we're gonna, let's just do it now. You're right. Yes. What I like to do in this course, in particular, because physiology I studied a little bit differently. And David, feel free to chime in whenever, man, if you have something to add. What I like to do is I always had a little binder, right? And I would have different sections of what I needed for that exam. I broke up the course by exam. So exam one, right? First, I'd have a printout of all the lecture slides, because that is really where the content and the information is located. Then I would have my own notes and in the next section. Then you guys should all have an ebook, right? Access to the ebook. I would print out the corresponding sections from the textbook, right? So if I'm reading about amino acids, right, and we're learning about amino acids, and Dr. Fried just finished his lecture on proteins 1, 2, and 3, and I took my own notes, right, and I have them in there. Then I would go get the textbook, find the section on amino acids, right, on proteins, print that out so I have that right there in the binder with me, because I'm not always in that. Again, I like pen and paper. I'm kind of old school like that, but I like to have it all in one place. In the next section, I have all the practice questions, right? All the practice questions for exam one, just one after another, just so I can have them all and look at them in a row. Now, to answer your question, practice questions are going to be your best friend. You're going to want to look at older ones that you're provided. You're going to want to find new ones online. You're going to want to look in maybe your MCAT books, if you guys have them. Look on some websites for your MCAT type questions, right? Because those are going to be formatted in a way that really force you to think and understand the concept. And especially if you're prepping for the MCAT, you're killing two birds with one stone there. But yeah, practice questions, it's scientifically proven to be the best method of study, by practicing, practice, look for those questions when you're learning about material. If you're learning about protein structure or pH, we'll stick to this topic, pH. When you're learning about the logarithmic scale, make up questions in your own mind. Think, okay, how could she word this into a question on the exam? How could she present this to me in a way that is going to force me to think? Ask your own questions, write out your own questions. Active recall is the second most effective way, according to studies, to learn their material, right? So some people use Anki. I'm not a huge fan. You guys know by now I'm a pen and paper type of person. You should see my stack of note cards from last year's. Like, it was like up to here. I just write the term, or I'll write a question. I'll put the answer on the back. But yeah, it's really going to be a lot of active recall, a lot of practice questions. Don't go into your book and reread. Don't look at the notes over and over and over. It's not going to stick. It's not going to work. Trust me. I've tried it plenty of times. I've wasted countless hours just rereading, highlighting. Useless. Don't got to do that. Rewatching lectures, like, just binge watching lectures like it's a new TV show that came out. I'm just one after the other. Not going to work. You're going to have to assess yourself. And again, I'm going to just bring it back to the science of it. Studies show if it's harder, if it's more uncomfortable, it sticks. It sticks more. People don't like studying because it's hard and it's difficult and it makes you work and you have to think, and nobody wants to have to do all that work. But the harder it is and the more questions you're getting wrong, you're like, oh man, I want to get that wrong. The more you're struggling, the more you learn. So do with that information what you will. Don't go crazy, but there's no secret.
Okay.
There's no secret formula. Just do the work.
Just to touch on to the Stevens ideas. For me, I like using Google Docs a little bit more than pen and paper. And something that really helped me is, rather than waiting until when the review sheet is sent out, use the objectives that are given before each lecture, like in all the PowerPoints, put them onto like a doc if that's what you want to do, or pen and paper, and then start defining all the terms, start making your own review sheet. Because by the time you get the actual review sheet, if you did more than necessary, that's amazing, good for you. If not, okay, like, worst thing, then now you have the review sheet, and you can supplement anything you're missing, and you can see what you need to work on. And yeah, the more practice problems you do, the better. And one more thing, for me, I really like knowing what the etymology of the word is. Like, for example, if you got a random enzyme name and you have no idea how to pronounce it, for me, I never remember the name of the enzyme until I actually know what the function of the enzyme is. So I used ChatGPT a lot last year. I just did define this word, or like, what is the etymology? That really helped. It's made the terms less foreign for me. Obviously, don't go crazy with that. But like, yeah, like, supplement the information in any way you can, like in a reasonable way. And also, like, we're here for you. The teachers are here for you. So like, always free to reach out. And yeah, like, you guys are gonna be great.
And I'll tell you guys what, David's methodology of going by objective rather than chronologically of what the professors were doing was brilliant. Like, it kind of changed the game for me too. Like, we were friends last year too, David, and he was kind enough to make up that document. And I think at the end of the year, it ended up being like 250 pages or something, but he would go by objective. So exam one, he'd have the objective and explain everything that was relevant to that objective. And I used that as a resource more than anything else. Like, I can't even tell you how helpful that was for me. And in fact, I liked it so much, that's how I'm going to be running, or how we're both going to be running these review sessions. We're not going to go, we will be going slide by slide, but there's going to be a focus on the objectives. Why? Because the objectives are what matter, and that's what's going to be tested. And no, it's not all about the grades, it's not all about the testing, but we want to do good on the test. And there's no shame in that. So we're going to do whatever we can to help you in that regard. Are there any other questions before we jump into it?
I have a
I got
question.
a quick question.
Sure. I saw you, and then I'm not sure who the other person was, but you can
It's
go.
me, Belinda.
Belinda, hi. All right, EM and then Belinda hopping. Yes, sir.
So the study guide that she had uploaded to Canvas, would that be a good resource as well?
Oh, of course. Anything that Dr. Peterson is providing, I would trust. I can't say that, for everybody. I've had professors in the past, not necessarily here, but like in college or undergrad or my other MBA program, and they've just given me stuff I don't need. Right.
Did
But
she? I'm sorry. Did she give you guys these study guides when you took it before, or
oh yeah, well,
did they help?
let me just preface all that with this is a very different course than what it was last year, right? Because we had a different course director last year, Dr. Pinto. He was great, but there was not as much focus on providing practice questions or study guides or resources, right? Dr. Peterson actually was loved by our whole class just for that exact reason, because she provided us everything we needed. I didn't have to think about, what do I need to really focus on? What's going to be on the test? Whatever. She gave us that information. Like she was in charge of cholesterol metabolism and all of metabolism at the end, integration of metabolism where everything comes together. And she figured it out. Sorry, someone to say something. Anyway, she laid it all out perfectly. So use anything that Dr. Peterson provides. Of course, anything the other lecturers provide, definitely look at them, use them. Our whatever we're providing, David and I, is strictly supplementary. Whatever you're looking up on the side, your MCAT stuff, your own notes are supplementary. But whatever she gives you is fair game. So yes, if it's on that study guide, you may be tested on it. So I would learn every letter on that sheet.
All right, thank you.
Sure. Belinda?
Yeah, hi.
Hi.
I just would like to know generally how long are these sessions gonna last?
We're looking about an hour and a half, right, David? An hour and a half. Sometimes maybe less, a little bit more. It kind of depends on the week. This one might be a little bit shorter. But then it might go the full hour and a half, even a little bit longer because of this whole introductory portion. But you should consider it about a lecture worth of time. And again, no one's mandated to be here. You come and go as you please. I'll be happy to readmit you if you have to dip out for a second and come back. It'll all be recorded and posted on Canvas. So this is just a little bit of a supplement to your learning.
Okay, thank you. So just letting you know, I might need to switch devices later on, so just let me back in later.
Yeah, sure, no problem. Just pop right in and it should show me on the screen to readmit you.
Okay, thanks.
No problem. Any other questions? Okay, so I do like to make this a little bit of an interactive experience. It won't be too, I'm not going to try to put anyone on the spot directly, but I would appreciate if you guys would I'm going to ask questions. I'm going to say, okay, finish this sentence for me, or you're going to see on the screen, help me out. If you know it, answer it. If you don't know it, try to answer it. No one's grading you here. No one's judging you here. This is where we learn. Again, what did I say? By getting the questions wrong and by struggling and by being like, oof, it sticks better. So do yourself a favor and try. If you have questions, feel free to ask me. Just interrupt me right there. Just, oh, wait a minute, Steven, blah, blah, blah. You don't got to call me like TA Steven or whatever. That just Steven's fine. Steven, Steve Areno, whatever you want to call me, man. It's cool. All right, so you know what? Let's just jump right into it. I'm gonna go ahead and share my screen. We can get started. Oh, I'm sorry. We have some questions in the chat. Sorry, Freda. How many hours did you spend studying for the class? I think we'd probably be better off using our metric as days. Yeah, it adds up. It adds up. And again, Freda, I wouldn't put it into terms of how many hours I put in, because you know what? There were times where I'd put in 10, 12 hours a day and I wouldn't learn nothing. Right? I'd be sitting there just reading and reading and reading and watching, and I'm technically studying, right? but it was useless. So I would say it doesn't matter. Some people can learn all the material in 2 hours. Some people like me, it takes 8 hours, right? It's a matter of learning the material. If you can look at a slide, ignore the text portion, right? Just look at the title, and you can explain to me what is going to be said the same way that Dr. Peterson would, or one of the lecturers, then you're good. Then you can move on, right? But just putting in the hours means nothing, you know. And I was a victim of that same thinking for a long time. But you have to learn until you understand it, and you can apply it. And one method, one of my favorite methodologies is oh, I forgot the name of it. It'll hit me. But long story short, you explain the material to yourself or to somebody as if you were explaining to a 5-year-old, right? But you can still use the proper nomenclature. I have on my iPad where I take notes, I have a record feature. You should hear me. I sound like a crazy person. I'll be up. My parents will be like, okay, what is going on, man? This kid's talking to himself. But no, I have hours, dozens of hours of me explaining to myself the material. Why? Because sometimes, you know, I'll just look at a slide. I'll be, oh no, I know that. And then I get tested on it. I'm like, oh, I probably didn't really know that. I didn't know that actually as well as I thought I did. So I look at the slide. On that slide, I'll put the record button on. All right, so here we're talking about blah, 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 blah. And this is important because blah, 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 blah. And, you know, in the scenario where blah, 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 you know, I'll just babble on until I know I got it. Right. So it's up to you. Feynman technique. Thank you. Tanishka, I hope I'm saying that right. If I'm saying your name's wrong, please do correct me. I apologize. But yeah, Feynman technique, Dr. Feynman. I implore all of you to look into it because it really is marvelous. It does make a difference. And I did have to level up my studying skills substantially when I came into this program. You know, I had to learn the hard way a couple times, but you know, we made it here. So if I did it, you guys can do it for sure. Good. All right. Any questions before we get started? I am going to get rid of this. How do I turn myself off, actually? Stop video. Nobody wants to see all that the whole time. There we go. Okay. Hold on. All right, I'm going to just leave it on here and we can move forward. So, water pH and buffers by Stephen Yusuf. No, I'm just kidding. So this is going to cover lectures 1 and 2. Again, this is largely a review of things that you should already know. I'm going to pretty much just reiterate what was already given to you by Dr. Peterson in different terms. You know, it might stick differently, but this really isn't anything too crazy that we're doing here. Like the math problems, just do a few practice ones online. You know, it's really pretty straightforward. There's no mechanisms here. There's no long pathways like the Krebs cycle or protein synthesis that you have to memorize. This is not too shabby. This is not too bad at all. So let's start with the first objective, which is to review the properties of water important to life. Okay, who wants to just take a shot and let me know what your thoughts are here? Anyone have any thoughts on what some of the properties are that are important to life? How do I move this thing? There we go. Come on, don't be shy. Someone kick it off. Give me one property that's important to life. Why is water important? Let's just start with that.
It's polarity.
Polarity. Okay, so that's one of the properties that are very important. We'll get into that. Yes. Any others?
It's a good solvent.
It's a good solvent. Of what kind of molecules?
Polar.
Polar molecules, and that's a big deal. We'll get into that as well.
The properties that are important to metabolism are water soluble.
Yes, absolutely. Absolutely. Some of the major metabolic products and systems all take place in an aqueous solution and cannot take place in a different solution, right? So That's going to be really important. Terrific. Good.
I would also say hydrogen bonding and lipids, like non-polar things, are stabilized by water.
Absolutely. Let's go. Yeah. See, you guys know your stuff. You're killing it. I gotta figure. Oh, that's beautiful. Perfect. Excellent. Yeah. So you're absolutely right. So what's going on out here? Excuse me. Okay, yeah. So exactly what you guys said. You guys nailed it on the head. The solvent properties of water shaped the evolution of living things, right? This without water, nothing would have oh, there we go. We got more electrostatic interactions, changes in the colligative properties. Yes, you guys are on point. Absolutely. Yes. So, like we said, most small intermediates of metabolism, like nucleic acids, right? Like proteins, they're soluble in water. And that's important because it goes without saying that nucleic acids, which we know are the building blocks of genetic material like DNA and RNA, I'd say those are pretty important to life, right? So without the functionality of these nucleic acids, genetic information cannot be transferred or even expressed for that matter. Proteins, which are made from amino acids, which you guys are gonna love in the upcoming weeks, are what compose a vast portion of the biological machinery that allows us to carry out basically any function. Enzymes, which catalyze reactions and allow us to do things like break down food for energy or store that energy for fuel later, form tissues, facilitate major metabolic pathways like protein and fat and carbohydrate synthesis and breakdown to dispose of the toxic byproducts that those mechanisms yield, cell signaling, body repair systems, drug interactions, pharmacology, all of these things, anything you could imagine that happens in the human body or about the human body is in some way, shape, or form related to enzymes, and enzymes are proteins, and proteins need to exist in an aqueous environment. So we're not telling you this for no reason. It matters. Okay, Stephen. So you've told us why proteins and nucleic acids matter. What does that have to do with our discussion of water? Well, because these things don't exist in isolation. These proteins must interact. These amino acids must interact. Amino acids form peptide bonds with each other, which you'll learn, that form that primary structure, that chain, right? That protein chain, and then that protein chain interacts with each other with itself and with the water as well around it to make this the secondary structure. The tertiary structure, the quaternary structure is multiple proteins interacting with each other. So these things matter. These things matter. And okay, so we talked about proteins, we talked about nucleic acids, we talked about carbohydrates, and they also will play a role, we'll see very soon. What about fats, right? Lipid bilayers, the likely forerunners. Let me get my, do I have a laser on here? No. Okay, well, I got this over here. Actually, we'll use this. Yeah, now you can see it better, right? Lipid bilayers, the likely forerunners of biological membranes, form spontaneously in water and are stabilized by their interaction with it. What does that mean to you guys? They form spontaneously in water and are stabilized by their interaction with it. Lipid bilayers. It's no trick question. It's exactly what it sounds like. I'm basically, yes, they form on their own as a result of how lipids and water interact. You don't have to input energy. You don't have to do any work to make these things happen. It happens. Why? Because of the innate features, the innate chemical and physical and electrochemical properties of these molecules, proteins and lipids. So lipid bilayers, why are those important? And you're going to notice I like to break things down a little bit. I don't like to just, I like to really get into the nitty gritty kind of about why does this matter? Because too often we're taught information, right? You teach me something and I'm like, okay, when am I ever going to use this? I want to be a doctor. I want to be a dentist. I want to be a PA. I want to be a nurse. This does not have anything to do with anything that I'm aware of. Well, let me tell you. So that's why we're breaking things down. Lipid bilayers are what separate the inside and the outside of the cell, right? We all know that. Very important. Why? There are different concentrations of ions and substrates and proteins on either side of those of that bilayer. Yet I'm sure you've already covered some of that in physiology, or you will be soon at least, right? You're gonna have to know the different sodium concentrations, potassium, calcium, all these different ions, and that really, really makes a big difference. That is what gives an organism its structure, its organization. Otherwise, we'd just be a big pool of random macromolecules floating around and not really doing anything or interacting properly. The interaction between the outside and the inside of the cell is super important. Those concentrations are what allow us to have the action potentials, right? The sodium potassium pump, nerve conduction. These things make a difference. And that's because lipids are not water soluble. They're hydrophobic. They fear water, which we'll talk about. In fact, they hate water so much that they'll form spontaneously in water and will be stabilized by their interaction with it. These individuals have a common enemy. These lipids, these little soldiers of lipids, they hate the water. So they're banding up together and they'll form things like the lipid bilayer that we need so badly, or micelles, which you guys heard about in your lectures. And all that, it kind of speaks to the fact that although hydrogen bonds and ionic interactions and the hydrophobic effect are individually weak, their combined effects powerfully influence the three-dimensional shape and stability and consequently function of these biological molecules and structures. Super, super important stuff. And basically the purpose of this whole thing, like the theme of this whole first lecture. Any questions? Now, notice how we're going through the learning objectives. These are all of them for the first two lectures. As we go through, I'm going to highlight which ones we're going to cover next, right? Right now, we're going to do review weak interactions, including hydrogen bonding, and we'll cover these other ones next. So first, let's do hydrogen bonding. Before I get into hydrogen bonding, let's try this again. Let's see what you guys got here. What can you tell me about hydrogen bonding? Just give me whatever you got. Just shout them out.
They form between the oxygen of one water molecule and a hydrogen of another water molecule, and their weak interactions.
Absolutely right. And they're weak interactions. Very good. What else we got?
Hydrogen bonding gives water its unique properties, like having a higher boiling point, I
Yeah.
believe.
Absolutely right. The colligative properties, right? The boiling point, the melting point, the heat of vaporization. Very important. And also osmotic pressure, which we'll discuss. Also a colligative property. Excellent. All right. So you guys are getting the main ones. Let's go on.
Oh, I have another one.
Yes.
Although they're weak bonds, they are like dependent on the shape of them. So a stronger hydrogen bond is one that's straight, or I guess linear, and
Yes.
it's weaker.
Absolutely right. And that's actually a very interesting one. Remember that whole vector conversation that Dr. Peterson was discussing. Very good. Absolutely. Let's check the chat. What do we got? FON, yes, usually bond with the more electronegative of the elements. Absolutely. And electronegativity, we love that word. Yep. Fluorine, nitrogen, oxygen in terms of the strongest bonds. Yes. Yes, I'm sure you guys studying for the MCAT are familiar with the whole Funkelbusch.
And I would say that hydrogen bonds, they usually happen with like alcohols, aldehydes, ketones, the peptide groups, stuff like that.
Absolutely right. Yes. Wow, you guys must have been really paying attention out there, unless you're looking at your slides. No, I'm just kidding. You guys do it. You can do whatever you got to do. I love this. I love it. You guys are doing a great job. Absolutely. So let's jump in. Yes. The come on. There we go. Hydrogen bonding. Hydrogen bonding, as we said, gives water its unusual properties. It has a higher melting point, a higher boiling point and a higher heat of vaporization than most other common solvents. So when I ask what is a hydrogen bond, you guys answered with the correct answer. It's an electrostatic attraction between the oxygen atom of one water molecule and the hydrogen of another. Now I know also fluorine and nitrogen are also capable of taking part in hydrogen bonding. From a biological perspective, really it's just oxygen and nitrogen. You know, you never really see too much fluorine. It's a pretty dangerous chemical. You might see it in some pharmaceutical, you know, products, but otherwise, no. But in terms of water, we're just talking H and O. So yes, it's going to be the electrostatic attraction between, come on. Oh, but this is even better. I don't know what it is. No. There we go. Between the oxygen atom of one water molecule and the hydrogen of another. Now, what phenomenon causes this to happen? Someone explain to me why that happens. How come that oxygen and that hydrogen are attracted to one another?
Isn't it due to electronegativity and also the dipoles?
Bingo. Bingo. Electronegativity. Yes. That is the key here. Now, when I say electronegativity, sorry, one second. Let me just. There we go. Yeah, it all boils down to the concept of electronegativity. And I'm speaking specifically about the electronegativity of the oxygen. Electronegativity is an atom's affinity or will to collect electrons. How badly does that atom want the electron, right? And that all just goes back to kind of your valence shells and your you know, all the basic chemistry stuff. We're not going to get into that right now, but the valence electrons want to fill up their shell, and oxygen is super electronegative. So with that said, it's going to want to pull in that oxygen or that electron that the hydrogen has on it, right? And in doing so, we're looking at, as you said, exactly, yes, a dipole. And we should also note that those electrons, right, they're all going to be huddled up around here. They're all going to be huddled up around that oxygen because we have a greater pull of electrons, right? So what does that mean? We have a dipole, we have a partial negative on this side, and now the hydrogens here, which are devoid of our electrons that we need, now we have a partial positive. And get familiar with this concept because it does matter. And as a result of the concentration of all these negative particles around this oxygen, it's going to confer a bent shape over here of 104.5 degrees, right? 104.5 degrees is what, it's the main number you guys got to know, bent, right? Let's also really quickly take a look at the hydrogen bond and covalent bond length, right? They are quite telling. What does this say to you guys? When I look at this, hydrogen bond 0.177 nanometers and covalent bond is 0.0965 nanometers. What does that tell you about the hydrogen bond in relation to the covalent bond?
Well, covalent bonds are shorter, which makes them stronger, whilst hydrogen bonds are farther apart, which makes them weaker.
Absolutely right. You're absolutely right. Yes. The covalent bonds are shorter, which means they're pulling a little bit harder, right? And we have to remember covalent bonds are sharing. They're sharing bonds. They're very different from hydrogen bonds. And hydrogen bonds are also fleeting, right? Break, reform, break, reform, break, reform. That kind of compromises the strength as well. So just to give you a little perspective of where we stand in terms of different bond strengths. So when we say hydrogen bonds are relatively weak, we can always take a look at that dissociation energy, the bond dissociation energy. And this is not going to be a huge portion of the lectures, but it does give you a little bit of a perspective. About 23 kilojoules per mole in liquid water. That is the bond dissociation energy, the amount of energy required to break the bond. Not a tremendous amount. And as I said, they are fleeting. They are there and then they're not. And this happens extremely quickly. So the lifetime of each hydrogen bond is just 1 to 20 picoseconds in the liquid. When one breaks, another one forms. And this just keeps on happening over and over and over and over again. Easy enough. Now, remember when we said that these forces, these hydrogen bonds, are weak individually, but they're pretty darn strong and effective when working in conjunction with each other. So logic would dictate that more bonds means more strength, right? So let's take ice. We know that ice is a very solid substance, right? You punch it, you're gonna hurt your hand. You punch water, you're Gucci. You ain't gotta worry about nothing. We know that ice is a pretty solid substance and that it's much more difficult to agitate or manipulate than liquid water is. And why is that? Well, it's because in liquid, each water molecule forms hydrogen bonds with an average of about 3.4 other molecules. But in ice, we're looking at about 4 hydrogen bonds, and that will help to form this lattice structure that you guys are looking at over here. This lattice crystallized structure. And that is not only going to be responsible for the increased stability and strength of the water as a whole, but it's also actually going to be the cause of the whole water expansion theory, right? When we talked about you put something in the freezer or a can and it explodes the next morning. Oh man, I forgot to take it out. Right? It's because of this lattice structure developing, and that's actually a very unique property to water. And this is all due to the number of hydrogen bonds that can be formed. Now, let's talk a little bit more about the thermodynamic end of things. You know, I had on these slides, I had it like sequenced so that you can go, you know, it shows one part and the next part and the next part. And for some reason, that's not doing it now. But, oh, you know why? Because I'm not in the full screen. How do I do this? Come on. Oh, there we go. Look at me. I'm learning as we go. Okay. Good. Yeah, now it's working. All right, terrific. So, hydrogen bonds account for the relatively high melting point of water. During melting or evaporation, heat is taken up by these systems, and the entropy of the aqueous system will increase. We'll wait to get into the thermodynamic portion of these things. Okay, there we go. Enthalpy, roughly talking about the heat content, roughly reflecting the number and kinds of bonds. No, this is not the quote unquote technical definition that you're going to find in the old school textbooks. No, it's a bit more complicated than that. But for the purposes of this lecture, enthalpy is heat. Okay, we're going to stick with that. Heat content, you know, the type of bonds being broken and formed and all that. Oh dear. I apologize, guys. Did I just cut out for a moment? Hello?
Yeah, it's glitching a bit, and now I think I don't at least I don't see the PowerPoint on your screen anymore.
I'm sorry. I think I had bad connection for a second. Let me go back. Screen share. Do I sound better now? Is this any better?
Yeah, you sound clear now. It was just the previous slide you sounded a little off.
All right. Did you guys hear the enthalpy part?
Honestly, since you started talking about the slide, it was a bit laggy, if I'm being honest, but that might have just been me instead of the other guys.
Well, no problemo. I'm glad you said something. Let's go. All
Thank
right.
you.
No problem. Thank you very much. And I'm sorry if that happens again, guys. I'm just having a few different issues on my end, but we'll get that cleared up by next week for you for sure. Anyway, so what I was saying here was during the melting or evaporation processes, heat is taken up by the system and the entropy of the aqueous system increases. So what does that mean? We will get into the thermodynamics a little bit more moving forward. Entropy, enthalpy, Gibbs free energy, and all these things really they play a big role in terms of favorability of a reaction, right? In terms of disorder, in terms of bond breaking and forming, reverse reactions, all that. So definitely get a good idea of what this all means. It is important. Oh, I do have a laser pointer. Nice. Look at that. Okay. Notice here though, these numbers. This tells us it takes more energy to go from solid to liquid, to go from liquid to gas than it does to go from solid to liquid. Only takes 6 kilojoules per mole to go from a solid to a liquid to melt. And it takes a little bit less than 9 times more to go from a liquid to a gas. And that makes sense, right? Because I like to think of, when you're thinking about including heat into a system or including energy, I like to think the molecules are moving a lot more quickly, right? They're going really fast in the gas, and they're bouncing all over the place in the liquid. They're still moving around, but they're more fluid and chill and doing their thing. And in the solid, they're just not moving, right? So that is going to, but that means more disorder for me, right? When I see a bunch of gas particles bouncing around and flying all over the place, I'm thinking, oh wow, look at the chaos, look at the disorder, look at the entropy of this aqueous system, right? Let's keep that in mind as we move forward. Enthalpy. Now, enthalpy for our purposes is going to be heat content. It roughly reflects the number and kinds of bonds. Again, this is not the super technical definition. This is going to be more, for our purposes, heat content is enthalpy. Okay, we're not going to go too much deeper than that. And free energy, G, of a closed system equals enthalpy minus temperature times entropy. Enthalpy, entropy. So H represents enthalpy, T is temperature, the absolute temperature, and S represents entropy. Now, who can tell me what the value of a delta G can tell me about a reaction? Who remembers? We didn't talk about this in lecture, really, but it might help tie some things together. If I have, all right, we'll just put it this way. If I have a negative delta G, what does that mean?
Reaction is spontaneous.
Boom. What does that mean?
It's exergonic.
Yes, you're right. Sorry, you're right. But when you use the word spontaneous, what is that definition like? So when a reaction is spontaneous, what does that mean?
It's
Energy.
energy.
I'm sorry, repeat that.
Energy is released.
Well, that's more like the exergonic
The
portion.
products have less potential energy than the reactants.
Also true. So yes, you're all to give me the right answer. I'll just tell you straight up. It means that the reaction can move forward without putting in any energy. Spontaneous means it's gonna happen. It might not happen today. It might not happen in a minute. It might take 1,000 years to happen. But if the delta G is negative, it's gonna happen. And you don't have to put any energy into it at all. If the delta G is positive, that means it's favoring the reverse reaction. The reaction is going this way instead of this way, right? It's not a huge part of the test, but it might help you understand, what we're doing moving forward. Okay. Water forms hydrogen bonds with polar solutes. Yes. Hydrogen bonds will form readily between an electronegative atom, aka the hydrogen acceptor, and the hydrogen atom covalently bonded to another electronegative atom, or the hydrogen donor. Right? So here we have the acceptor, the hydrogen acceptor, and here we have the donor. Yeah. Because this molecule has the hydrogen being transacted, right? This is the one being given back and forth. So this is the donor, the one giving, and this molecule is receiving the hydrogen, right? To become a hydroxyl group. Now, as we all know, water is not the only place where we see hydrogen bonds forming. They can readily form between an electronegative atom and the hydrogen atom, you know, covalently bound to another one. So that's fine. But there are rules to hydrogen bonds. There are rules. And I'll let you guys take a look at this diagram really quick before I jump into what those rules are. Can anyone remember what one of those what that rule is, the main one that we talked about in class? Hydrogen atoms that are covalently bound to an electronegative atom can form hydrogen bonds, except in what case? What atom bound to a hydrogen doesn't count? Carbon, absolutely right. Hydrogen atoms covalently bounded to carbon atoms do not hydrogen bond. Why? The carbon atoms are simply not electronegative enough to carry out this phenomenon. So if you see some carbon atoms bound to hydrogens, and we ask you, can that form a hydrogen bond? The answer should be no, right? Over here we can, over here we can, over here we can. Why? Because we have a nitrogen, we have an oxygen, nitrogen, oxygen, oxygen, oxygen. Those are all good. Oh, here's a carbon and a hydrogen. I don't see any blue lines over here. You guys get it. Also, as somebody wonderfully mentioned before, alcohols, aldehydes, ketones, and compounds containing NH bonds are also going to form hydrogen bonds with water. Like down here, for example, when we look at our nucleic, our bases, right? Here we have an adenine and the thymine, and they can form hydrogen bonds, and they can also form them with water. Any questions? All right. Well, I have a question for you. I want to give you it's a little bit of a long one. I'm gonna give you 2 minutes. Okay. And you know what? Let me try to see if I can figure out how to do a can I do a poll here? Come on. All right, you know what? I'm gonna have to figure out how to do the whole poll thing. Come on, man. Yeah, all right. Well, this is not working. You guys answer this question, and I'll just give you the answer momentarily. And I'll explain why afterwards. But for your own good and for your own personal satisfaction, do try to figure it out. I'll give you 2 minutes. All right. Hopefully you guys have had enough time to take a look. Let's go through them. Which cannot hydrogen bond? Well, we know that we're going to have, we have this nitrogen. Nitrogens can hydrogen bond. So that's good. That can. FH, that can hydrogen bond. Yeah. That can hydrogen bond. We have the oxygen. Nitrogen. Yes. OH. Yes. Oh, sorry. What about E? Can that hydrogen bond? I don't see any O's. I don't see any F's. I don't see any N's. No, that can't hydrogen bond. H. Yep, we got O's. We got an O and an H. K. Yes. C. Oh, I'm going down and up. Sorry. It's all right. This looks good. This looks good. Uh-oh. Not seeing what I got to see here. Boom. Can't hydrogen bond here. Absolutely not. Why? We got all carbons here, man. We got all carbons. It's not going to work. And this is good to go. Are there any questions about this before we move forward? Does that make sense to everybody? And if there's something in the chat that I'm missing, just let me know. I'm not quite sure how to check that. If I go here. Yeah, I probably have to escape that here. Uh-oh. Cat 31. Oh yeah. Oh yeah. Oh yeah, we're getting some good answers over here. Okay. Let's go back. Good. One moment. Let's go back. Okay. Very good. Move forward. Directionality of the hydrogen bond. We did speak about this before, right? One of the reasons the hydrogen bond even forms in the first place is because the H bond itself has a dipole. Yeah, so this bond here has a dipole. So this portion will be partially negative. This portion will be partially positive, right? And someone so adequately mentioned before that the shape matters, right? So looking at these two atoms here on the left, we see that they are in a straight configuration, and that would give us a strong hydrogen bond. Yeah, they're strongest when the acceptor atom is in line with the covalent bond between the donor atom and the H. Who can tell me which one is the donor and which one is the acceptor? Is this the donor or is this the donor?
The OH is the donor.
Alcohol is the donor.
The top, yes, this is the donor here. This will be giving, and this will be receiving it. And we also, Dr. Peterson did mention vectors. You see how this one here is in a bent configuration this way, makes it weaker. Yes, the vectors are an important aspect. I am not the greatest mathematician in the world, so I'm not going to get too into that. I don't want to confuse you guys more than I have to. But this is the main point. Yeah. Any questions here? We're good. Good. So we covered hydrogen bonding. I think we're good on the hydrogen bonding part. This is going to play a big role moving forward as well. So definitely do know your stuff. Now let's talk about those hydrophobic, hydrophilic interactions and the hydrophobic effect as well. So let's start with hydrophilic. Wait a minute. Who can tell me what hydrophilic is before I show you that?
Hydrophilic are the water-loving molecules.
Yeah, exactly right. Hydrophilic describes compounds that dissolve easily in H2O, and they're generally going to be charged or polar, right? Because water is polar. Like dissolves like. So, polar compounds, charged compounds, and those will be our hydrophilic. They love, filed, it's the Greek word for to love, phili, hydro, water, just like David said, break down the etymology. Who can tell me hydrophobic? And give me an example.
Hydrophobic would be water hater. It would be non-polar like pentane.
Terrific. Yes. Hydrophobic. Water fear. Water fearing. I'm arachnophobic. I hate spiders. So, hydrophobic. They're afraid of water. They don't like non-polar molecules. We're looking at our non-polar molecules usually, and that's going to be our like lipids or waxes and some of those other inorganic substrates that exist. We're not going to get too into those. And then finally, we have the lovely amphipathic. Amphipathic. Who can tell me what an amphipathic molecule is? And give me an example. Fernando.
Properties of
Oh boy, we got a few. Fernando, yeah, I think you just answered. So whoever the other person was, go right ahead.
they have properties that are both of both hydrophilicity and hydrophobicity. And an example of that could be phenylalanine.
Beautiful. What about another example? Anyone got any other examples?
A phospholipid bilayer.
Boom. That's what I was looking for. That is what I was looking for. The phospholipid. Come on. Isn't it doing it? Yeah. Contains regions that are polar or charged and regions that are non-polar. Yep. Phenylalanine, the non-lipid, the lipid bilayer, excuse me. They have the hydrophilic head, hydrophobic tail, the hydrocarbon tail, right? Look at that a little bit more later. But yeah, amphipathic is going to come up again a lot. So you're not going to hear any other way of referring to it. You're going to hear amphipathic, and you guys should know what that means. Here's some examples. Glucose, polar, right? You can dissolve sugar in water. That's how I like to think of it. Glycine, aspartate, lactate. Lactic acid buildup in the body can spread out. It can dissolve in the water. These are all polar. Non-polar, typical wax. Nope. Amphipathic, phenylalanine, as you said. They're gonna have a little bit of both, right? Because these are going to be your polar groups. This is your non-polar group. Phosphatidylcholine, which you guys are going to see a whole lot in cell signaling and a lot next year as well. Phosphatidylcholine, phosphatidylethanolamine, and all these other big fun words that make you sound really smart when you talk to your friends. And let's just really jump into, based on what we just talked about, water as a solvent. Yeah. H2O dissolves salts and charged biomolecules by screening electrostatic interactions. What is an electrostatic interaction? Who can tell me?
Is an attraction between molecules with opposite charges.
Absolutely right. Yep. Hit the nail on the head. It is the attraction between opposite charges or the repulsion between like charges, right? It's exactly right. And the increase in entropy of the system is largely responsible for the ease of dissolving salts in water. right? And remember how entropy means disorder. Yeah. The universe, and this is something you should remember as you move forward, the universe is always moving toward a state of more entropy. The universe wants disorder. To make something ordered, to make something more organized, more structured, usually you need to put energy in. You have to input energy or do work of some sort to reintroduce order into a system. But one of the main laws suggests that the universe is always moving toward a state of disorder, of entropy. So this increase of entropy of the system is largely responsible for the ease of dissolving salts in water. You dissolve the salts in the water, that means they can break up, ionize, and there's more disorder. Yeah, good. Water has a high dielectric constant. Now, this dielectric constant is a dimensionless physical property, and it's going to mainly just reflect how many dipoles are in a solvent, right? And just to give you a little bit of perspective, for water at 25 degrees standard temperature, we're looking at a dielectric constant of 78.5. And for a nonpolar molecule like benzene, for example, a benzene ring, we're looking at just 4.6 as a dielectric constant. Don't get too bogged down with the details here. Just know that it reflects the number of dipoles in the solvent. That's really all that you're responsible for knowing over here. You don't got to remember these numbers. You don't got to remember the specifics here or how to calculate these things. But you should know what it is. What is it referring to? Number of dipoles. Easy enough. Now, this is going to tie back in a little bit later, right? Nonpolar gases are poorly soluble in water. And our most biologically important gases, right? Carbon dioxide, oxygen, in its in this molecular form, O2, I think I'm using that right. There we go. And nitrogen are nonpolar. And that means they're going to be insoluble in water, or rather really poorly soluble in water. And here's a little chart for your own reference to look at later. You don't got to remember any of these numbers or constants or anything like that, but they don't dissolve well, and that'll tie in a lot more in the buffer section, and especially the blood buffering mechanism that we talked about, because these are really important. These are important. We need these for survival, and I really hope I don't have to explain why. But if I do, I'm sure you'll understand by the end of this lecture. And again, their movement into aqueous solution decreases entropy by constraining their motion. This kind of speaks to what we've talked about before, their movement into an aqueous solution. Oh, if you just mute for me, that'd be great. I'm sorry, whoever just came in. Thanks. It's going to constrain their motion, right? You go from the outside world and a bunch of space into an aqueous system. They're going to be much more constrained, thus decreasing their entropy, decreasing the disorder, increasing the structure and order, right? Now, nonpolar compounds are going to force energetically unfavorable changes in the structure of water. Okay, so what does that mean? Energetically unfavorable. We just talked about that, right? In terms of Gibbs free energy. What is unfavorable? A positive delta G or a negative delta G? Unfavorable.
Positive.
Positive. So yeah, nonpolar compounds are going to interfere with the hydrogen bonding among water molecules and increase the enthalpy and decrease the entropy. Now, let's look at the equation. Here's our equation. Delta G equals delta H minus T delta S. We know what all these numbers stand for, or all these letters, excuse me. The free energy change, right here, represented by this equation, for dissolving a nonpolar solute in water is unfavorable. In other words, it's not going to happen unless you input energy. Delta H has a positive value, positive. Delta S has a negative value. Delta G has a positive value. Delta G has a positive value. By that information, right, and one more of these constants, you can figure out the other. I'm not going to go through the math of this. Feel free to work it out on your own time. But it does work out, right? Now, as I just said, you have to, this is unfavorable. You can't dissolve a nonpolar solute in water. Why? Because it's not going to happen on its own. But if you include some energy, right? If you put in, you have some energy input, then you can, it alters this equation, right? You put in some temperature, it might alter the equation, or in a way that does push this into a negative. Again, I'm not going to go through the arithmetic of it. It's pretty straightforward if you just go, on a whiteboard and work it out. But that's probably why things break up a little bit better when you use heat, right? When you heat up your tea, or your when you're in the lab and you're heating up a solution and you want it to dissolve quicker and better, you're inputting some heat, you're inputting energy, and that allows for this delta G to become a little bit more negative and a little bit more favorable, right? It allows for the reaction to proceed in the forward direction. Does that make sense? Good. Now, let's talk about the ordering of water molecules around nonpolar solutes. So, these water molecules are going to form very highly ordered cage-like shells around each solute molecule, each nonpolar solute molecule, I should say. Why does it do this? Because it's going to maximize solvent-to-solvent hydrogen bonding, right? You're going to have more bonding between the water than you will instead of it bonding with the nonpolar substance. Because, again, a nonpolar and a polar substance are not going to like each other. They're going to want to stay away from each other, right? So here we can see that here. An amphipathic compound in aqueous solutions. So now we're going to see the best of both worlds. We got that polar hydrophilic region, that hydrophilic head group, which is going to be exposed to the water, whether it be the inside of the cell or the cytosol, or the ECF, the outside of the cell. And that's going to be exposed to water, and that's totally cool because this is hydrophilic, this head group. It interacts favorably with water, and it tends to dissolve, right? If it's a dissolvable compound, that is, right? The head group is not going to dissolve, obviously. On the other hand, we have this non-polar hydrophobic region, this hydrocarbon tail, the alkyl group, as we call it, which you'll learn plenty about moving forward into next semester as well. And these want to avoid contact. These guys are all staying apart from each other. They're not on friendly terms whatsoever, right? So they're going to cluster together and kind of huddle around this non-polar region, and understandably so. Highly ordered water molecules form cages, as they call it, around the hydrophobic alkyl chains. Easy enough. The hydrophobic effect. The hydrophobic effect is exactly what it sounds like. It's when nonpolar regions cluster together and polar regions arrange to maximize interactions with each other and with the solvent. And you can see that pretty clearly over here. And here we see those micelles that we were talking about, right? Where'd you guys go? Hang on. One minute. All right, well, I can't really see you guys anymore. I'm not sure why, but that's okay. Polar regions arranged to maximize. Yes. Oh, so here are these micelles we were talking about down here. Thermodynamically stable structures of amphipathic compounds in water. You got the the hydrophilic on the outside, and you got the hydrophobic on the inside. And these micelles are going to become actually really important when we start talking about fat metabolism, lipid metabolism in the digestive tract, right? And bile and cholesterol and your fat soluble vitamins and whatnot. These become very important in the transfer of those lipids from the GI tract and into the bloodstream. And you'll know all about that by the end of the next year. But for now, I'm trying to explain to you, why are we telling you all this stuff? And why am I reiterating the same old stuff over and over and over again? It's because it matters. So we covered that. Don't worry, these move a little bit quicker than all this. We did the hydrophobic interactions, the hydrophobic effect. Now let's talk about some van der Waals interactions. And that's also called London dispersion forces. And who can explain to me quickly what is a van der Waals force? A van der Waals interaction. Just do the best you can.
They're distance dependent interactions. They never touch. That's all I can remember.
All right, yeah. So I'm gonna be honest, you broke up there a little bit, but it sounded good. It sounded all right. So yes, distant dependent, weak attractions and repulsions between transient dipoles. Keyword transient. It's important. They come and they go. These dipoles are going to exist, and they're going to move, and they're going to not move, and they're going to be going back and forth, but they'll never touch. These atoms are never, the van der Waals radius is the measure of how close an atom will allow another atom to approach. They'll get really close, but they won't touch. So if we have two molecules, right, or two atoms, and there's a dipole, yeah, so there's a partial positive and a partial negative, that partial positive can attract the partial negative of another of the same atom, thus causing an attraction, right? Or it can be a repulsion if it's the same charges. It actually is much easier than a lot of people make it out to be. It's a pretty simple concept, but just the way the textbooks explain it is it can get a little bit excessive. But don't think too much into it. It really is just exactly what it says here: the attraction and repulsion between transient dipoles. Again, you don't need to know all these, it's just for reference. So why do we keep on mentioning all these different things that I thought we would never ever have to use again when I was taking Gen Chem? It's because now they matter. Now that we're at the point where it really does become crucial in terms of macromolecular structure and function, right? These non-covalent interactions are they're not strong individually. They're weaker than a covalent bond, for example. But when you put them all together, man, they are the maestros. They are the conductors. They are what orchestrate the formation of major components of basically every system. Yeah. And we'll get into that a lot more. You'll see a lot of that when you get into proteins and how the different primary, secondary, tertiary, and even quaternary structures interact as a result of these forces. Hydrogen bonding plays a huge role in protein folding, and there's other interactions as well between side chains of the amino groups and all those different the backbones and whatnot. And this is all going to make a lot more sense in the coming weeks. So don't worry if you're not 100,000% sure right now about what these things are all meaning and where they all fit in, because they will fit in very soon. So yeah, that's why we keep on mentioning these things. And again, they're continually forming and breaking. You're going to see, as we see here, hydrogen bonds, ionic interactions, the hydrophobic effect that we saw where they make a little cage, van der Waals interactions when you have two atoms in close proximity with one another. And, they have dipole interactions. These are all going to play a role, and they're all referred to as non-covalent, weak interactions. And that's something that you should definitely keep in mind. These are non-covalent, weak interactions. All of them: hydrogen bonds, ionic interactions, hydrophobic effects, and van der Waals interactions. The cumulative effect of weak interactions. So for macromolecules, this is the the more stable structure is usually the one that has the most weak interactions. And then Dr. Peterson was mentioning, if you look at this image down here, it testifies to just how tightly water molecules are going to bind to the actual structure itself, just how integral and how important water molecules are to the actual structure, and even sometimes the function of these biomolecules, right? And if you take a crystal structure like in the lab, they'll even show up in there. If you're familiar with the whole crystallography of certain molecules, this will resonate quite a bit with you. If not, then don't lose sleep over it. This is just to illustrate a point that water and weak interactions have a huge role to play in biomolecules. I'm saying the same thing over and over again right now. In future weeks, it's going to move a little bit more quickly, right? A little bit more fast-paced than this, and a little bit less redundant. But now we don't have tons to talk about, but we're doing what we have to. Questions before we move forward? Okay. So we did spend a little bit of time, a little bit more time than I had hoped in the beginning, discussing the introductions and answering some questions and going through some study tactics and whatnot. So we might go a little bit longer than anticipated today, but that's fine. If you have to go, then go. If you can stay, then by all means, you're more than welcome. But I'm going to go through this whole thing. Okay. So water can be essential to protein function, as we just said. Here's an example of cytochrome F. We're going to see cytochrome F in all kinds, or cytochromes in general, and all kinds of different biochemical mechanisms and pathways, like most notably the electron transport chain. Yes, right at the end of cellular respiration, we get the electron transport chain where we can yield that ATP. And with the ATP synthase, I hope some of these words are resonating, because you're going to need to know all this not soon, but in the future for sure, definitely within the scope of this class. Detox pathways, oxidative stress relief processes, like cytochromes play a big role all over the place. This one in particular has a chain of 5 bound water molecules over here. Here's the rest of it. And these may provide a path for protons to be able to move through the membrane. So water is literally a part of this protein. Without the water, this protein is not complete. That should tell you, it should further testify to how important water is in terms of the human body, in terms of cellular function, protein function. Like, even at the smallest level of one single protein, the cytochrome, water is a literal piece of it. This blew my mind when I first read about it. I had no idea. I thought it was just surrounding all this stuff, but it's literally a portion of the actual protein. Amazing. Okay, let's jump into the osmotic pressure and osmosis terms like hyper, iso, and hypotonic. So we talked about the colligative properties already. Solutes will alter the colligative properties of the solvent. Yes, solute is the thing being dissolved. The solvent is the thing doing the dissolving, or water would be a solvent in this case. And those colligative properties are vapor, pressure, boiling point, melting point, or freezing point, which we already discussed. We're not going to get back into that. Also, now we have what's called osmotic pressure. Osmotic pressure. And this is pretty darn important, you know, and it is dependent upon the number of solutes or a number of solute particles in a given amount of water. What's another word for that? What I just said, the number of solute particles in a given amount of water.
Concentration.
Concentration. Concentration. Exactly right. The concentration is what is going to determine the osmotic pressure. And we all know what osmosis is. I really do hope so. Just movement of water across a semi-permeable membrane driven by differences in osmotic pressure. Okay, just water. Osmosis. Osmosis Jones. Okay. So, who can explain this diagram to me? You can stutter, you can stumble, you can have a hard time. I'm really curious to see who can explain to me what is happening here. Or someone start off and then someone finish off, or someone work together. Come on. Like I said, you have to try and you have to fail to learn. This is the place to do it. You don't want to do it on test day. Come on.
So I think what's happening is the water is going through the semi-permeable membrane.
Yep.
Because it wants to go from a high concentration of water to a less concentration of water, smaller concentration.
Not of water. Of what?
Molecules.
Yes. You're exactly right. You're exactly right. So yeah, over here, down here, we have that semi-permeable membrane, allowing only water to get through. And this is all pure water, nothing else in there. And in this tube, we have a solute. Doesn't matter what it is. It could be salt. We'll just say it's salt, right? So what do we know about the movement of water? It moves from what concentration to what concentration?
High to low.
High to low. The water moves. The solute's not going to move. The water's going to move. So the water out here, it's saying, oh my gosh, there's a high amount of concentrated substance in here. I better rush in there. I better rush in there so that I can get a state of equilibrium, so that I can help maintain homeostasis in the system, right? So the water here, as shown in diagram in part B, is going to rush in to help equalize until we can get a relatively equal balance, right? Now it's going to go up to a certain point. So we're going to provide an equal and opposite force using a piston, right? Just a little like a weight to push it back down. The amount of force, right? The amount of force that we need to bring it back down to water level is going to give us that osmotic pressure. So if you see this diagram on a test, you should be able to understand, and you might not, it might not even be on the test, who knows? But you should be able to understand what osmotic pressure is, what drives it, and how we could measure it. Yeah? Are there any questions about this diagram here? All right. So the effects of extracellular osmolarity on water movement, this becomes super important also in terms of physiology as well, and pathopharmacology. Like I said in the beginning, biochemistry is important in all the bigger more complex studies. So here we have the effects of extracellular movement. Here we have our intracellular solutes, our extracellular solutes over here. This is isotonic. We got about the same amount of black dots from the outside as we do on the inside. Equal movement going in and out. Isotonic. Yeah. Hypertonic. Who can tell me what hypertonic is? What is a hypertonic solution? All right. We'll just put it out there. It's pretty straightforward. It's on the
It's a heavier concentrated solution than what's inside of the cell, and it forces the cell to shrink in the end.
Exactly right. Hypertonic solution means higher osmolarity, more concentrated on the outside than on the inside. And as a result, the water will rush out to compensate for that difference, and the cell will shrivel up. And hypotonic, it's already here on the diagram, so I won't ask you guys, but that is a lower osmolarity than that of the cytosol. And if that happens, we're in trouble because those cells can burst if we get too much water in there. And Dr. Peterson was also mentioning, this becomes super important when it comes to administering medication or drugs or anything for that matter into a patient's circulation, into a patient's system. Because if you have a hypotonic solution in the bloodstream, right, that's a problem because their cells are all going to explode. And I'm sure I don't have to explain why that's a bad thing. Okay, so we covered a lot of the water part. Yeah, let's talk about some of the more empirical portions of this discussion. So pure water is slightly ionized. Pure water is slightly ionized. What does that mean? Ionized. Well, it's in the word ionized, to become an ion. Yeah. So water molecules have a slight tendency to undergo reversible, forward and backward. They can go in either way. Reversible ionization to yield a hydrogen ion, which we all know is just a proton, and a hydroxide ion. Right? And this is what we're gonna stick to. Okay. Now, in reality, we know the hydrogen ions are immediately hydrated to form a hydronium ion. Don't pay too much attention to all this. Be aware of it, okay? Because technically, this is a little bit it's a little bit confusing if you think too much into it. But I need you guys to focus on this portion here. All right, water will break down into an H and an OH. Simple as that, right? H plus and OH minus. We're going to stick with that moving forward. Proton hopping. So proton hopping is basically when protons can move from one location to another very quickly. Right? This is going to be important when we talk about acid-base reactions, and the conductivity of electricity has to do with proton hopping, among other things. Right? So you can get a hydronium ion to give up one of its protons, and that can just bounce, hop all the way over to here and generate a hydronium ion on this side. Just be aware of what that means. Equilibrium constants. Now, this is where we get into the nitty-gritty. This is where we're going to start talking about the where all the main concepts that we're going to talk about come from, right? We're going to talk about the basics. So an equilibrium constant is the KEQ, which you guys should have already learned in Gen Chem. If not, then definitely just go back and brush up. That'll give you the position of equilibrium for the generalized reaction. Question higher. All right, good. So A plus B becomes C plus D, and back and forth. And if we are talking about concentrations of the reaction, right, we're going to define it in terms of concentration of reactants and products. It'll be in this fashion. Products, C and D, over reactants, A and B. And that's your KEQ. KEQ. When you see K, think equilibrium. And this is a constant. See, products over your reactants. Any questions there? That clear? Good. Okay, so the ionization of water is expressed by an equilibrium constant as well. Okay, so this is the equilibrium constant for the reversible ionization of water. So KEQ, equilibrium constant, equals products over reactants. Now remember, over here, we talked about the ionization of water, right? Products, reactants. Products, reactants. Products, reactants. Always going to be products over reactants. So KEQ equals concentration of hydrogen times concentration of OH minus over the concentration of the water. And we know that the concentration of pure water, unadulterated, is 55.5 moles per liter. This is a known constant. It's just information that we have, right? So here's the breakdown of it. Just know this, 55.5 moles per liter. Now, the ion product of water. So if we want to figure some more information out, right? And we have this information, we have the concentration of pure water. We already have that, right? Because we have this, we can figure out the rest. Or at least if we have a couple other variables. You don't have to know how to do all this for the exam, you know, like you should, but it, you know, these specific, when I say these specific numbers, you don't have to know all of this exact stuff, but be aware of how we're getting what we're getting. Okay, so KEQ equals products over reactants. You rearrange it into this fashion here, and you get what is called the KW, the ion product of water. The KW is the ion product of water. Now, let's try to calculate this. Okay, in pure water, the KEQ is 1.8 times 10 to the negative 16th. Okay. If we substitute our value, so now we know the concentration of pure water, and we know the KEQ. We know the concentration of pure water, and we know the KEQ. That means we can figure these out because we know that these are going to be exactly the same stoichiometric proportions, right? 1 to 1. Sub in the values, rearrange, do whatever math you got to do. You end up with a number of 1.0 times 10 to the negative 14th molar squared. 1 times 10 to the negative 14th. This is important. Go ahead and put these in the chat. I'll give you 30 seconds. No, I'll give you 45 seconds. Feeling good today. All right. We got 11 answers in here. That's no good. Come on, guys, wake up. 8:41. We're getting there, I promise. But yeah, you guys killed it. Absolutely right. The answer is D. And here's the work for it. Feel free to come back and look at it. KW equals concentration of H plus, concentration of OH. You rearrange. We know these numbers. We know that the KW is 1 times 10 to the negative 14th, which we talked about. And we know that the concentration of the OH is going to be 1 times 10 to the negative 2. Dr. Peterson mentioned about the way that you handle an exponent when you're dividing, just subtract, right? Done. Okay. Neutral pH. What does that mean? What's neutral pH? Someone tell me. All right. It's exactly when you have exactly equal concentrations of your protons and your OH minus molecules in pure water. Pure water is neutral pH, pH of 7. And at neutral pH, we are going to see over here 10 to the negative 7 molar. Right? This is the same thing that we just covered. Don't worry too much about the math over here, but at neutral pH, that is what we're looking at. 10 to the negative 7 molar of both the H plus and the OH minus. And that becomes important. Now we're talking finally about pH. pH, super important. The pH scale is based on that ion product of water, that KW that we just talked about, which we figured out is at neutral is 1 times 10 to the negative 7th. Here's the expression that we use to determine pH. Right? We know that H plus, the concentration of H plus, as we just said, here, 10 to the negative 7th molar is here. So to get the pH, you take the negative log, right? You just take the negative log and that'll give you the pH. Here's a little table showing you all the different pHs. So if you have something that is 10 to the negative 9th molar, you're looking at a pH of 9. And there's also POH, right? You could do the same thing that instead of having an H here, you have the OH minus, and that'll give you the POH as well. But we're going to work mostly in terms of pH. And again, a neutral solution at 25 degrees Celsius is 7 pH. So if we're looking at a pH value greater than 7, is it going to be acidic or basic? Basic. Alkaline, basic. Concentration of OH minus will be greater than that of H plus. And on that basis, we know that the pH values less than 7 will be acidic, with a concentration of hydrogen ions greater than those of OH. And again, here's a little scale, you know, it'll give you a nice little overview of what stands where. Here you got hydrochloric acid all the way at the top or the bottom, if you look at it in terms of pH. And those are that's super acidic, right? We're going to see that in the stomach, right? The cells of the stomach will secrete that, and that's why we have such a super acidic environment in the stomach. That's why we have that mucosal lining around the stomach to protect it from the acid breaking down the tissue. If we didn't have that lining, this acid would eat right through any type of muscular tissue. And we, you know, as we go down, you know, here's gastric juice, right? Because it's not just hydrochloric acid. There's other juices in there as well. But gastric juice is going to be super acidic. And then as you get into the duodenum, we're going to shoot some bicarb in from the pancreas. And that bicarb is gonna neutralize the acidity a little bit more. Yeah, it's not on here, but you get the idea. Once you go into the small intestine, we have to kind of bring down the acidity a little bit. Anyway, I'm jumping ahead of myself, but just to put it in terms of physiology, just so you understand. And all the way down here, you got that NaOH, which is super basic. You guys do need to know that. You must know, at the bare minimum, hydrochloric acid and NaOH, sodium hydroxide. You guys should know that those are super acidic or super basic, you know, respectively. in terms of, yeah, so in terms of pH and medical diagnoses, which is where we're really headed to apply all of this random math and equations and constants, we want it all will affect medical diagnoses, medical conditions, and it makes a big difference. So when the pH of blood plasma, which should be 7.4, drops below that figure, or too far below that figure, the patient becomes acidotic, right? You'll see that in uncontrolled diabetes, particularly diabetes type 1, where patients can develop an obscene amount of ketones, right? Because they can't process the glucose, they can't break down carbohydrates, so they have to resort to breaking down fat. And that fat breakdown, that fat metabolism produces what are called ketones, right? Like beta hydroxybutyrate, acetoacetate, acetone. You guys will learn more about that later next semester, but it's because of these ketones, which are highly acidic, that these patients' blood levels drop. The pH of the patient's blood levels drops, and that becomes enormously dangerous, right? And this is we'll talk about why as well. And on the other hand, on the other side, we have what's called alkalosis, right? And that's when you have a pH of blood plasma above the normal value, which is just as bad, super dangerous. And it's important as we talk about buffers, we'll talk about how we can maintain our pH within a healthy, reasonable level. But it's really important that we stay within the physiologically appropriate range. Otherwise, we're in a lot of trouble. And yes, it can absolutely be life-threatening. Absolutely. Are there any questions there so far before we move forward to pKa? Okay. So weak acids and bases have characteristic acid dissociation constants. Acid dissociation constants. Okay. A conjugate acid-base pair, bringing it back to the Gen Chem, is a proton donor and its corresponding proton acceptor. Yeah. So the stronger the acid, the greater the tendency to lose its proton. The stronger the acid, the more fully it will ionize, the more it'll break down, right? So I'll let you guys look at this for a second. Excuse me, I just got to grab my charger really quick. Okay. Okay. So yeah, we're good. So we talked about the stronger the acid, the greater the tendency to lose its proton. We know that some different things have multiple protons that they could lose, right? So here we have monoprotic acids, one proton, monoprotic, like acetic acid or the ammonium ion, and they can lose one of their protons. This proton here can pop off. We have diprotic acids like carbonic acid, right? H2CO3, and those diprotic, two protons, diprotic acids, they have the potential to lose two protons. And that'll happen at different stages. I'll tell you more about that when we get into the pKa's. But you can lose one proton from carbonic acid and it turns into bicarbonate, right? And then that bicarbonate has another proton that it can lose, right? So we'll get more into that. And there's also triprotic acids. I'm not going to get into those too much. Now, the ionization behavior of water and of weak acids and bases dissolved in water can be represented by one or more equilibrium constants. Okay, we'll talk about those. Now, remember, the equilibrium constant is going to be the Ka. The Ka. We spoke about that in lecture, and the Ka is going to help bring us to pKa, And the interaction of pKa with pH will tell us whether something will be protonated or not protonated. I know it's kind of a lot to process at once, but once you really you start applying it and doing some practice problems and re-looking at it, it'll all make sense. Now, most biomolecules are ionizable, and what do I mean by ionizable? They can be broken down into ionic or into different ions, either positively or negatively charged ions. And their structure and function will depend on their ionization state, whether it's positive, negative, or neutral. And that is characterized by our equilibrium constants. And here are the ionization constants, right, that we gotta take a look at. The tendency for any acid, and from moving forward, when I say acid, when you hear acid, think of it in terms of HA. H being the proton, A, just being whatever the molecule is. HA, this is the protonated version. The tendency for the HA, the protonated version, to lose a proton and form its conjugate base. This is the acid, this is the base. The acid and the conjugate base, A minus, is defined by the equilibrium constant KEQ. We're bringing it back to KEQ. Remember all that? And we know that with KEQ, we're looking at products over reactants. Products over reactants. Right? HA breaks into H plus and A minus. So here are our reactants. Here are our products. Here are here's our reactant. Here are our products. Easy enough. You plug them in. And now this KEQ, it has a different, we call it Ka in terms of ionization constants. When it comes to acids and their conjugate base forms, Ka. Okay, very similar. These are very synonymous, but they do represent different things. So be aware. Ka. So back to this chart. Every substance, right? Every acid has a Ka of its own, right? And they're all determined, right? So now that we know what Ka is, we're gonna apply it to the big one. This is the big dog, pKa. And remember what we had pH, right? And we had to deal with the negative log. This is the same deal. It's analogous to pH, and it's defined by this equation. pKa equals negative log of Ka. When you see that little p in the front of it, usually it means negative log of, right? So P negative log of Ka. Negative log of Ka. Does this make sense to everyone? Does anyone have any questions? Okay. In the future, we're going to probably take a break in between sessions, but this time, we did run a little bit over in terms of the introduction and beginning and whatnot. So the stronger the tendency to dissociate a proton, the stronger the acid and the lower its pKa. Understand this. So a strong acid will break down much easier. It'll dissociate much easier than a weak acid. And if you have a strong acid, the stronger it is, like like hydrochloric acid, right? It's going to have a very low pKa. And since this is a negative log, it'll have a very high Ka. So strong acid, low pKa, high Ka. And we can determine this experimentally, right? With the burette and whatnot. I'm not going to get too into that because it's not going to be tested, I don't think. But for those of you who are still awake, thank you for staying. Go ahead and answer this question. I'll give you 30 seconds. I know we did these in class already, but I really want you to look at them again, okay, before we get into some different questions and really understand why, you know. All right, yeah. Yep, you guys got it. It's a weak acids only partially ionized water. We're getting there. We're getting there. We're getting there. I promise. Time to apply it now. Titration curves. Titration curves reveal the pKa of weak acids. Okay, this titration curve is for acetic acid. We'll see it again later. And this is a plot of pH on the y-axis here against the amount of sodium hydroxide being added. Right, so we're going to add slowly. We're going to add some sodium hydroxide. And we're going to observe the changes in pH as we add the sodium hydroxide. Now, this becomes important, right? So let's just jump right into the thick of it. Two reversible equilibria are involved in this process. We don't got to focus. This is the water one. Yes, it's involved, but right now we care about this one here. We care about this reversible process. The equilibria conform to their characteristic equilibrium constants, right? So we already know the Kw, the equilibrium constant of for water is 10 to the negative 14th. The Ka here for acetic acid in particular, again, products over reactants, when you're thinking equilibrium constants, products over reactants. This is it. 1.74 times 10 to the negative 5th. That's for acetic acid. So when it's all said and done, we're left with this curve pretty much over here. And at the midpoint, the pH of the equimolar solution, in other words, we have equal amounts of hydrogen ion and equal amounts of hydroxide, OH minus. When we have equal amounts of both, they're the same thing. At that pH, we have the pKa. Here, right here is our pKa, right? 4.76. This is our pKa, just below 5, right? Now, using that pKa, using that number, this is where the buffer part comes in. This is the buffering region. We're going to go exactly 1 pH unit up and 1 pH unit down. So if we're using acetic acid as a buffer, it'll be best to keep a solution within the range of 3.76 and 5.76. Why? Because the pKa is 4.76. You go down 1, you get 3.76. You go up 1, you get 5.76. So if someone's asking you on an exam, which substance would be best used to buffer within and keep something within the range of 7 and 9, you would want a pKa of what? 8, right? A pKa of 8, because that'll be 1 up and 1 down between 7 and 9. That is likely to be on the test. So, be aware of this buffering region protocol here, be aware of what it means, the relationship between the pKa and the pH and the buffering region. These things make a difference. Right. And you can, just for further, clarification, we can compare the different titration curves of 3 different types of weak acids. Right. So here for NH4 plus, it's going to be a little bit higher. It'll have a buffering region between 8.25 and 10.25. Why? Because the pKa is 9.25. Same with this one. Same with this one. A weak acid and its anion, or a conjugate acid-base pair. Know these terms. Conjugate acid-base pair is simply a weak acid and its anion. They can act as a buffer. Now, what's a buffer? It's a aqueous system that tends to resist change in pH when small amounts of acid or base are added. Yeah. It's going to help keep you within a certain range. And again, like I said, the way you select a buffer is based on what pH range you want to keep the system in. We want to resist any major changes or fluctuations in pH because, as we know, a too high or too low pH can result in denaturation of vital proteins and functionality as a result. Okay, we discussed that already. The weak acid is the proton donor. We know that. Conjugate pair is the proton acceptor. Question. Is the midpoint the same as the equivalence point? I want to say no. But Rach, I will get back to you on that, and I'll include that. I will include that in the slides that I post. All right. Let me just get a little document going where I can put some good questions like that one. I don't want to give you the wrong. I think I know the answer, but I want to be 100% sure and give you a nice little. I hope you guys like my background. Anyway, I want to give you guys a very clear answer, so I'll post that for you, Rach. David, it was what's is the midpoint the same as the equivalence point?
So to answer that, it depends on the acid. For example, like acetic acid is a monoprotic acid, so therefore the midpoint is going to be the equivalence point because if you look at the x-axis on the graph, you can see the titrants, the equivalence of OH added, which is the amount of base. So then once you reach 0.5 equivalents of base, right, that's when you reach pKa, which is when you have 1/2 charge of acetic acid. Whereas let's say you take phosphoric acid, which has 3 donatable hydrogen groups, you're going to see 3 different pKa's, and then therefore 3 different equivalence points at each different buffering region. So it really depends on the acid, if that makes sense.
There you go. Thank you, David. All right. I hope that answers your question, Rach. Either way, I'll still post an explanation regardless, just so everybody can check it out later. And let's move on. Perfect. So here is that acetic acid acetate pair. Acetate, when you hear ate at the end, like instead of salicylic acid, you hear salicylate. That is usually just a deprotonated form of whatever the acid is. So acetic acid would just become acetate, just for future reference. So which one is the donor and which one is the acceptor? Who can tell me? Is this the donor? Is this the donor? Just type it in the chat. I can check it. HAC or AC minus? Correct. Correct. Yep. HAC is the donor. Good. Let's try this one. You guys are good. Yeah, it's A. And this becomes important in the muscles, for example, right? When you have lactic acid buildup, right? If we didn't have the bicarb buffer system, we would do a sprint or a couple squats and boom, you're acidotic and on the brink of death, right? So if we have the buffer system, that it prevents that from happening. It lets us do a lot more. Very important. So an aqueous solution of a weak acid and its salt makes a buffer that resists change in pH in response to added acid or base. The weak acid in this case would be the donor. The salt would be the acceptor. Biological systems are going to be buffered to maintain a narrow pH range in which their macromolecules retain their functional structure, which depend on their ionization state. Now remember, pH plays a huge role in protein structure. You go too high or too low, the proteins, they'll denature, they'll lose their shape, they'll lose their functionality. And I know I've said it 100 million times already, but there must be a reason for that, right? So we also know that the conditions that produce blood pH outside of a range of 7.3 to 7.5 are going to be life-threatening in humans. Easy enough. Henderson-Hasselbalch. This is going to be a big one. So the Henderson-Hasselbalch equation is going to describe the shape of the titration curve of any weak acid, right? That's the formal definition. The way I like to look at it is it's a great tool to help you figure out any one of these variables, assuming you have a couple of them already given to you, or a couple of them already. This Henderson-Hasselbalch equation is very helpful in giving you either the pH, the pKa, the products, the reactants concentration. You can figure those all out based on this equation. All right, so become familiar with this. Look for practice problems with this. Do know how to derive information from that equation. Since we are running low on time, I'm going to go ahead and skip this one because it's going to take a little bit of. We did that in class already. You can feel free to go ahead and check. Just to give you the answer, it's D. Right? If you have the pH and you have the Henderson-Hasselbalch equation, you can figure it out if you're given the pKa. Yeah. You can figure out the concentration of the acid and its conjugate base using the pKa. Now, weak acids or bases buffer cells and tissues against pKa. pH changes. Said the same thing again. Here we were given the example of histidine, which is an important amino acid, and you can always tell histidine because of its side chain. You got this little ring-like structure over here, and histidine has a pKa of 6.0, and that means it will buffer effectively near the neutral pH, near 7. So if we have something that we want to keep between 5 and 7, right, we can use histidine because it has a pKa right in the middle of 6. Now there's two main buffer systems you guys should be aware of. First of which is the phosphate buffer system. We're going to see that in the cytoplasm of all cells. It's outlined over here, pretty straightforward. Acts as a proton donor, the H2PO4, and the HPO4 2- acts as a proton acceptor. So, as we talked about, up one, down one. And the big one is the bicarbonate buffer system, which acts in the blood plasma. And we definitely want to keep within the right range here. And it's actually it's pretty accurate in terms of keeping it in the right range. The H2CO3, the carbonic acid, acts as a proton donor, and the bicarbonate acts as the proton acceptor. And here are some additional equilibrium constants. Carbonic acids formed from dissolved aqueous carbon dioxide and water in a reversible reaction. Now, I emphasize the reversible part because we do have to be able to go back and forth, right? In terms of breathing, we got to get it in and out, and the fact that it's reversible allows for this buffer system to regulate pH in both directions, right? We can make something that's too acidic more basic, something that's too basic more acidic, by manipulating this equation. And the brainstem will do that by altering breathing rates and things like that. Okay. So the pH of the bicarb system, the bicarb buffer system exposed to a gas phase, depends on the concentration of HCO3 minus, the bicarbonate. So yes, concentration matters, and the partial pressure of CO2, the concentration of carbon dioxide in the gas phase, because we need that pressure. Remember how we talked about how these insoluble gases, they're not soluble in water, right? They're not friendly with water. As a result, we need that extra push. We need that force, that pressure, to be able to move the CO2 and into or out of the body. Yes. So it involves 3 reversible equilibria here. As I said, the rate of respiration controlled by the brainstem can quickly adjust these equilibria, 1, 2, 3, to keep the blood pH nearly constant. That's how we keep it so accurate, right? Because we can use these equilibria, we can manipulate them in a way that allows us to use that pressure that we talked about, that buildup, that PCO2, PO2. You're going to learn a lot more about this as well in your physiology class, and of course here, and it'll tie together a little bit more. I know I'm giving you bits and pieces now, but it'll all tie together, I promise you. And so bottom line, the partial pressure of CO2, the PCO2, equals the concentration of CO2 in the gas phase. Okay. So if you're hyperventilating, that's going to raise your blood pH, right? Because you're pushing all that CO2 out. You're moving the CO2 from here, and you're bringing the pH back up, right? If you're acidotic, you're going to see your ketoacidosis patients, right? Your diabetic patients, if they come in with ketoacidosis, they're going to have those, what are they called? I believe they're called Kussmaul respirations. You're very quick, shallow breaths, trying to push out all that CO2. Why? Because if you move in CO2 out of the system, you're lowering the acidity in the blood. Yes, AM. Hey, there we go. There we go. All right, good. Yeah, so you guys are on board. You understand? Perfect. That's exactly why when DKA happens, yes, diabetics have the Kussmaul respirations, trying to expel the CO2 out and thus remove the acidity from the bloodstream. Bravo. Very well done. Yes, absolutely right. And you see how all these little things, they seem kind of boring and redundant in the beginning, but eventually we can apply them to a clinical setting. And, ideally, if you grasp these concepts, if you really understand them well, it can make the difference between saving a life in the future. It really can. So I'm glad you guys are following. Excellent. Calculating blood pH. We have our typical values. So a lot of the time they will measure these values in the plasma. Doctors will do so in a clinical setting to get a little bit more insight into how the patient is dealing with different levels of pH and acidity in their blood and whatnot. Can be very telling, but we're not going to get too into that right now. And from these typical values, right? So we have the carbonic acid, right? Our reactant. We have the bicarbonate, our product, right? Our conjugate base. And from these values, we can determine things like pH, pKa. Yeah. And if you just do the math over here, it brings us to our optimal, these are optimal numbers here, and that gives us our optimal blood pH. Okay. Any questions there? No. Okay. So we're nearing the end. We're nearing the end here. Untreated diabetes produces life-threatening acidosis, as we discussed. An optimum pH equals the characteristic pH at which enzymes typically show maximum catalytic activity. The pH at which the enzymes work the best, so to say. So notice here how pepsin, which helps to break down peptide bonds, help break down proteins, is more effective where? At low pH. Catalytic activity is almost at 100, or pretty much at 100, when you're at a pH of between 1 and 2. And where are we going to find that? In the stomach. But if we had active pepsin working at this level in the bloodstream, which has a pH of 7.4, woo, we'd be in big trouble. We'd be in big trouble because I know there's quite a few important proteins, right, in the bloodstream. So if we got a bunch of pepsin floating around at this pH of 7.4, we're donezo. Notice how it's not active. It's not at all active when we get to this level here. So these different enzymes have different pHs at which they function best. Trypsin, which we'll also learn about, it functions much better at near and neutral pH. And these all have a reason. These all have a reason for the way they function. And it really is miraculous. Like, it's beautiful the way it's all set up. Like it's like an orchestra. I'm telling you, it's incredible. Now, as we said, diabetes mellitus, acidosis, high concentrations of the 2-carboxylic acids, beta hydroxybutyrate, acetoacetic acid. You don't have to know these now. You will have to know them, but right now, don't worry about it. Ketones. That's why some people on the keto diet, they'll check their ketones, right? And that's just an indication of whether you're burning fat instead of glucose for fuel, right? The dissociation of these acids is going to lower the pH of blood plasma to less than 7.35, which, as we know, is bad. Are there any questions? Anything at all? I don't know why the chat's not showing. Hold on. There we go. No. Okay, good. So let's just wrap it up with a few practice questions. Really quick and easy ones. I'm not going to give you any math stuff right now. We may post some mathematic type questions in the future, but these are really easy to find. Close. Yeah, 104.5. 104.5 is the number we were looking for. But the 9 looks close enough to a 4, so we'll give you partial credit. But yeah, 104.5 here. Degrees, helpful to know. What is pKa? Shout them out or type them in the chat, whatever you want to do. What is pKa? At what point would we have the pKa? Yep, the negative log of Ka, that's the equation. But what is it? Think about it in terms of the concentration. There we go, Julia. You got it. You got it. It is when we have the pH at which the proton donor's concentration is equal to the proton acceptor concentration. Or in other words, the concentration of H plus is equal to the concentration of OH minus, as shown in this titration curve here. Excellent work. When would a patient be considered acidotic? Under what conditions? What pH conditions? AM, there you go. All right, you caught it in time. Yeah, so 7.4 is optimal. We can actually get down to around 7.35 and be all right. But of course, if they ask a question on the exam, it'll be much more obvious. It'll be like 7.1 or 6.9 or something, at which point the patient will probably be dead. But yeah, the pH less than 7.4, 7.3. If you said that, you're correct. Yes. But yeah, around less than this, acidotic, dangerous, bad, needs treatment. Okay, let's move on. Why is acidosis a problem? Why is it bad? We know it's bad, but why is it bad? Enzyme shut down. What's a good word for that? Denaturation. What does that mean? Denaturation. Proteins unravel. Man, we got a good group. We got a good group here. This is excellent. You guys are making my job easy. Enzymes and proteins denature and thus lose function. They cannot maintain their three-dimensional structure. Right. We'll talk more about that as we get into Dr. Freed's lectures. Excellent. What is a buffer, and what do they consist of? There are two components to a buffer. What are they? And what does a buffer do? Beautiful, Tanishka. Yep. Excellent, Freda. Yep. What do they consist of?
Acid and its conjugate base.
Beautiful. Excellent. Yep. You guys got it. Buffers are an aqueous system that tends to resist changes in pH when small amounts of acid or base are added. And it consists of a weak acid, the proton donor, and its conjugate pair, the conjugate base, the proton acceptor. Excellent. Oh, well, I guess I didn't put the right animation on this one, but which one's the donor, which is the acceptor? Pretty straightforward. We know this already, I'm sure. What's the buffering region?
It's like the flat area on the titration curve.
Yep, it is. And in terms of region that operates within plus or minus 1 pH of, not the buffer, of what? The pKa. Correct. Plus 1 or minus 1 pH units of the pKa. Here's our titration curve. Here's that flat area that we were talking about. Plus 1, minus 1, and that's our buffering region, right? So you can add a whole bunch of OH equivalents and still stay within that region. After a certain point, boom, you're going to skyrocket up. Okay. Which condition would cause red blood cells to burst due to excess water? I gotta, come on. Yeah, D. You place the cells in the hypotonic solution. We talked about that. We did this in class, but just gotta make sure you guys are paying attention. Whoa, look at that. Oh my goodness. Okay. So are there any questions before I stop sharing and before we dip out for the night? Thank you to those of you who stayed. I know it took a little bit longer than usual. I don't anticipate these will take that long moving forward, but we did have to cover a few housekeeping rules in the beginning. Nothing?
I actually have a question.
Sure,
In
go
the
ahead.
beginning, you went over how you study for this class, but how did you study for physiology?
Now, physiology, okay. Physio, I did a lot of flashcards. Physio, really, the flashcards were great. They it's a lot of terminology there. It's less critical thinking. They just tell you what's what, and you just memorize it. You just got to know, okay, the duodenum does this, and then this does that, and the brainstem works this way. So you can really just focus more on the memorization aspects of it. But yeah, with biochemistry, I, in my opinion, at least, and I'm the TA and I'm saying this, but biochemistry, in my opinion, is notably more challenging than physiology. Physiology is a lot of info, right? Physiology is fun. It's like it's really cool and interesting. Biochemistry, it's fun for me as well, but you must understand it for it to become like really exciting. There are some monotonous, boring subjects in here. I'm going to be honest with you. And if you don't know what you're talking about, and if you don't try to apply them into a practical setting, it's going to stay that way. But when you can figure out the big picture, now that's the key word here, big picture for biochemistry, then things start to fall. They start to fall together. In physiology, you're the human body. You know what the muscles do and what they are. You know about the kidneys and what they're supposed to be doing, right? They're just giving you the basics. But if you're doing biochemistry, we don't know any of this stuff, right? I took biochem. I took biochem in undergrad. Right? I thought I was hot stuff coming into this class, and I didn't know crap when I came in. I had to learn a whole bunch of new stuff. So, physiology, do what you got to do. You know what I'm saying? Just listen to the professors. It's very well organized there. Dr. Peterson, fortunately, is also very well organized. So you guys are very lucky this year. You're going to have excellent resources and excellent instructors. But other than that, it really does come down to whether you're going to work not hard, but rather smart. Work smart. Don't work hard. Nobody wants to be working their ass off 24 seconds. Do your thing.
Thank you.
You're welcome. And to answer your question, Julia, you've not taken biochemistry before. Well, you know what? The way I'd like to think of that is you haven't been adulterated by pre-existing ideas and notions. So now you're learning fresh, and you can learn it the right way and the hard way, right? You can learn the tough stuff, with a clean, fresh slate. Some of us who've taken biochemistry before, we're kind of corrupted by what our old teachers have taught us. So you got a leg up in that respect. So no, it's not going to be a problem. It'll be more foreign material to you, absolutely. I'm not going to deny that, but there's no reason that you can't perform just as well as someone who took 2 semesters in undergrad. Okay? You're welcome. All right, if there's no more questions, I want to thank you all so much, and you have a great. Oh, go
I
ahead.
have a quick question. Wait, sorry.
No.
How often are we gonna have these sessions with you?
They should be every week, right? Assuming that we have class. I mean, these are Sundays, so if we don't have any class the week prior, there won't be a session, but these should happen every week. All right, we're gonna figure out exactly what days, but it'll either be Friday at noon or Sunday at 7. But we'll let you know exactly what's going on and give you a very an in-stone schedule for you guys to refer to moving forward.
Got it. Thank you for your time.
Thank you. How did we do the first time? We did all right? Did I babble too much? Too little?
No, this was really good. Thank you.
I was a fan. Thank you.
You're a fan. All right, that's good. You make me blush over here. Thank you very much. Excellent. Well, on that note, if there's anything you guys ever want to see different, or you'd like me to change, or you'd like me to focus more or less on, I welcome and embrace criticism. So please do let me know. And other than that, I wish you all the best of luck. And my WhatsApp and my email are open to you. I'm here for you. Have a great night. Deuces. Much love.